All right, so it's Friday. We're gonna wrap up chapter 4 here. Okay. 1 week from today, you have your first midterm exam, and that will cover chapters 1 through 4. Okay. I'm not gonna answer like if you ask me emails like, do I need to know this specific topic? I'm not gonna give you a straight answer there. Okay. So basically, as far as the midterm goes, I'd say look at the material and content that was covered in the homework, look at the content covered in lecture, and that should get you pretty much through everything there. There might be 1 or 2 questions that will require some more thinking and more thought than what has been covered in the homework or lecture, but I think they're still very doable. Of course, I would think this, but I think all of my tests are fair. So, of course, I think that. So, okay. So let's wrap up chapter 4 here. Okay. So we left off and we said the correlation coefficient is equal to R, and we didn't get into the formula for calculation of R. Okay, so we did not cover manual calculation of R. Okay, but there is a concept where if you square R, okay, we get this value called the R squared value, okay? And this is called the coefficient of determination. And I should say R squared becoming big R squared, this applies only for linear regression, which is fine. That's the regression we've covered in this class. But if you were to take more statistics classes in the future or a class on regression, this relationship no longer holds. But anyway, we had this thing called big R squared, and that's called the coefficient of determination. So, let's say we have something that looks like this. Okay, and then we fit some kind of fit line here, something like this. And then we say R is equal to 0.9, okay? Well, then our R squared will be 0.81, right? Okay, so what does R squared, what is the significance here, okay? The coefficient of determination, this indicates the amount of the variation in Y that is explained by the variation in X. Okay? So let's say you have, I don't know, you are collecting data on, I don't know, how heavy a cow is, okay? How heavy is a cow, all right? And so and one of the things that we are going to use to kind of predict the weight of a cow will be its age. Okay, so we will try to predict the weight of a cow. Based on its age. Okay. So a linear relationship probably only holds for young cows, young bovine animals, because once they reach whatever, I don't know anything about raising livestock. So whatever age they reach maturity, they're probably not going to grow that much, right? Just like people, right? We grow through childhood, adolescence, and then we stop growing. Okay. So anyway, so linear relationship only holds for a certain time, and so we will assume that we're only looking at that time, okay? So the linear relationship holds only for a certain time range. So our data comes only from this time range. Okay. All right, and so let's say this is what it looks like. Okay, so on our x-axis we've got time or age, and then on the y-axis will be weight. All right. And so maybe for young cows or young bovine, there's a very strong relationship. Maybe r is equal to 0.9. Okay. So when we say r squared is 0.81, and we say this is the amount of variation in y that is explained by the variation in x, what exactly do we mean? So let me save this. This is week 3, Friday. Okay, so what this means is that if you think about what causes a young cow to weigh a certain amount of weight, there are a lot of factors, okay? Part of it is going to be how old the cow is. That's one of them. So we're recording that in age. But there's other things. What kind of diet is the cow on? Is the cow eating corn or grass or whatever? Okay. Maybe genetics. Did the cow come from a line of really big cows or small cows? Whatever. And just like individual differences, right? Like even cows born to the same set of parents may be different for all sorts of other reasons, right? So you can think of like there are a whole bunch of things going into determining how much a cow weighs. And what we're saying is that if r squared is 0.81, we're saying about 81% can be explained through age, okay? And we're not saying age is the sole factor or even something like that. We're just saying about 81% of the fact that, when you look at different cows, they weigh different amounts of weight. About 81% of that variation can be explained by the factor age, okay? There are lots of factors going into determining how much a cow weighs. And we're saying that age can account for about 81%, okay? So we're saying if, r squared equals 0.81, okay, so y would be weight of a cow, x would be age of cow, okay, and this is for non-mature cows. All right, so we're saying, there are many factors for example, age, genetics, diet, individual differences, etc. Okay? The amount of exercise the cow gets, I don't know, okay? Many factors that go into determining the weight of a cow. R squared equal to 0.81 says that about 81% of the kind of variation in weight. Okay, and so the remaining 19% would just be caused by the other stuff, is what we're saying. Okay? Okay, so let's try something here. Okay, and I will say x and y. All right, and I'll say okay, based on our regression analysis, so this will be a clicker question here. Analysis, we can explain 49% of the variation in y with the inclusion with x. Okay. All right, so I'm going to say estimate r. Okay. Yeah, you can talk. You can talk. Okay, we'll say 10 more seconds to get your clicks in. Five seconds. All right, click, 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 and we'll hit stop here. Okay, let's see how you guys did. All right, and indeed the correct answer is D. Okay, so the sentence 49%. This 49% of the variation can be explained. This refers to r squared being 0.49. Okay. And then so we know that r should be the square root of r squared, okay? And so this could either be plus or minus 0.7, right? So looking at the scatter diagram, we see that we have a negative relationship. So that means r must be negative 0.7. Okay? So yes, you know, the square root of r squared of 0.49 could be plus 7 or minus 7, but based on the scatter plot, we see there's a negative relationship, and that's why we do d is negative 0.7. Okay. Let's okay, let's cover a few warnings, okay? Warnings about the usage of linear regression. Okay. So number one, make sure the relationship is linear. Okay, which generally means make a scatter plot. Okay, so r squared, if r is anything other than 1 or negative 1, r will not tell us if the relationship is linear. Okay, so, if you were to create a plot that looks like this, okay, r is probably still going to be like 0.9, okay? But a straight line relationship is not appropriate, okay? A straight line is not appropriate. Okay, so don't try to use linear regression for this. Okay. Another warning: beware of outliers. Okay, outliers are not necessarily good or bad. Okay, but you should, anytime you create a plot, all right. So I'm going to just write this: beware of outliers. They can dramatically affect your analysis. Okay. So here's a silly example. Okay. Let's maybe we look at pizza consumption versus income, okay? So on the axis, we'll say we have income versus pizza consumption. So we ask, how many pieces of pizza do you eat in a month or a year or something, okay? Now, probably, I would not expect to see a very strong relationship, if there's any relationship, because you've got people with high income who eat lots of pizza. You have people with low income who still eat lots of pizza, and you got people with high income who don't eat pizza, and people with low income who don't eat pizza. So I would expect a very a trend not really to exist. Maybe the weakest of positive trends, because if you're like really poor, maybe you can't afford to eat pizza or something. But overall, I would expect almost no trend, right? Or I don't know. Does someone disagree and think that there would be either a positive or negative trend overall? Okay. So I'm expecting to see almost no trend. Okay. So let's say we surveyed just a bunch of regular old people, okay? Now, so here, if we tried to fit a line, we would get, almost no trend. Our regression line would be rather flat, okay? Now, let's say we surveyed Papa John, okay? And let's say he makes lots of money, all right? And I don't know. I imagine he eats a lot of pizza. Maybe this is not. Maybe this is not, like, because he's a real person, right? He shows up in all those commercials and he's like, whatever, I make pizza. Okay. So let's say he shows up out here. He makes millions of dollars a year, okay, because he owns Papa John's Pizza. And let's say he eats lots of pizza. I don't know if this is true or not. I should ask him. All right. If this were the case, then suddenly your regression analysis will try to accommodate the presence of Papa John, okay? And now, this is and now that Papa John is here, it seems like there is a definite positive trend between income and pizza consumption, okay? Or the opposite could also apply. You know, let's say in a different data set, you surveyed who is not going to eat pizza. Yeah, is there a prominent vegan? Michael Douglas? Michael Douglas, right? I don't know. You think he's vegan? Nobody even knows who that is. Okay. All right. Maybe there's like some really rich vegan person, okay? Crazy, out here on income, okay? And then, so now suddenly trying to, but eats no pizza, all right? Or eats whatever, okay? I don't know, all right? So the presence of outliers can drastically affect it, all right? And so if you have outliers, don't just say, well, let's throw them away. They're outliers. They don't count. You should always investigate the outlier and just say, like, what does this outlier mean, right? You know, if Papa John's in there, you go, oh, well, should I include Papa John in my analysis? And then you have to make a decision, okay? And you might say, well, because I have no other data for people with such high income, it would be unwise to include this. And that's a fine justification for removing outliers, okay? But you shouldn't just say like, this is inconvenient, so let's throw it away, okay? And I think sometimes the answer is do two analyses. One analysis with the outlier and one analysis without the outlier, or outliers, okay? So if outliers are present, okay, look into what they are. Okay? They could also just be typos, you know? Like somebody's punching in the thing, includes an extra 0, so, you know, rather than saying, oh, I ate 10 pizzas over the course of a year, I ate 100, okay? That's a, you know, or 1,000 pizzas, okay? That's a lot of pizza in 1 year. So, you know, if somebody just accidentally hit a few of the wrong keys or something, then you should throw that away, okay? So look into what they are, okay? Perhaps do two analyses. Okay, one with outliers and one without. All right. Okay, so beware of outliers. They can dramatically affect the analysis. Another one, do not extrapolate. Okay, or do not try to make predictions where you have not collected data. Okay, so here's a silly example. Okay, so let's say you have a child, and you're going to measure the child's height versus the child's age. Okay. And every year, you check the kid is growing, okay? And so, you know, at age, let's say you started this when maybe he was 3 years old and now he's 10 years old, okay? And then you say, oh, this kid has grown every single year from age 3 through age 10, okay? So based on this, I've created a regression analysis. The relationship looks linear, and so I'm going to predict that when he's 55 years old, he's going to be 20 feet tall. Okay? And we know that's silly because in reality, people will grow, and then maybe around age 17, age 18, or whatever, people stop growing, okay? So as far as height goes, this is the truth, is that people's heights stop growing, okay? So this could be, you know, so from age 3 to age 10, you know, so we witness annual growth from years 3 to 10, okay? But we cannot just project that this will continue on for the next 30 years, okay? And so, you know, as far as trying to predict the future, no one can do it, okay? We cannot predict the future, okay? So we might have very strong evidence that data we've collected in the past have shown linear trends, okay? But, you know, this is, if this represents now, so maybe we see a very strong evidence that a linear trend exists, okay? But what's going to happen in the future, okay? Will it continue on like this? Or, you know, will it steady off? Okay, or will it suddenly take off? We have no idea, okay? So as far as the future goes, nobody has any idea. All we can say is, you know, in the past, we have seen a linear relationship, okay? And maybe this can hold for the next 2 weeks, okay? Maybe it can hold for, maybe, you know, depending on what we're talking about, maybe we can make predictions maybe just like a tiny bit into the future, like a year into the future. But really, like, anything beyond that, we're really entering the land of mystery and the unknown, okay? I mean, just even talking about politics, nobody knows what's going to happen in November. No one can predict that with any kind of certainty. And, you know, if you look at where we are today in terms of the political landscape, and if you asked people, experts in the field, 6 months ago, if they would predict these results, most of them probably would not have, right? So, so as far as, you know, trying to predict the future based on what's happened in the past, this is a very hard thing to do, okay? So the future could look anything like this. I mean, it could even, this is certainly possible too, okay? We don't know, okay? So whatever it is, so really, all we know is that right now we're at this point, but in the future, anything is really possible, right? So that's called extrapolation. So, you know, don't do that. So I think it's very, you know, age versus height. It's very simple, but you know, we like to do stuff like this. We like to try to guess what's going to happen in the future based on what has happened in the past. So those are our warnings against the usage of linear regression, okay? Okay, so let's, I'm going to ask you a couple clicker questions here. Let's see how we do. Okay. Okay. You perform a linear regression analysis. Okay. You compare one of your data points to the regression model's prediction. Okay. So a negative residual means, okay, and your answer choices are, okay, we have made a mistake. Okay, our prediction was lower than the actual value. Then so your answer choices are: we made a mistake in our analysis. Our prediction was lower than the actual value of y. Our prediction was higher than the actual value of y. Or we are missing values to make predictions. Okay, so this is the question of what a negative residual means when you are comparing your actual data points to comparing one of your data points to the regression model's prediction. Question? Just one data point. One data point. Okay, we'll click stop in 5 seconds here. So get your clicks in. All right, let's take a look. The correct answer is C. Okay, so what is a residual? The residual is the actual value minus the predicted value. Okay, so it's E is y minus y hat. Okay, so if this thing is negative, okay, means that the predicted value, the actual was smaller than the predicted, right? So actual small and predicted is large. That's what we have. Okay, so the answer choice here is that our prediction was higher than the actual value of y. So meaning, if you've got some kind of prediction line here, the actual data point is down here. And so your residual is the distance from the prediction down to the actual. Okay, so the fact that the actual is lower means we have a negative residual. Okay. An interesting thing is that the sum of all residuals, okay, if you don't do any squaring, if you don't square the residuals and you just add them up, the sum of the residuals will equal 0. Okay, so I think someone asked, are we talking about the data in total? If we were looking at all of the data in total, the sum of all of the residuals would be 0. And that's just that's a property of when you try to minimize the square of the squared residuals, you end up getting this actual sum of the residuals to equal 0. Okay, so the sum of the residuals is equal to 0. This is and we try to minimize the sum of the squared residuals. Okay. All right, let's try another question here. Okay. So you look at the relationship between two numeric variables. Okay. The correlation is r equal to 0.95. And let's see. Okay. I will say x bar ends up being 10, y bar ends up being 8. The standard deviation of x is 3, and the standard deviation of y is 2. Okay? All right. So question 1, or not question 1, whatever. Here's the question. Okay. This will be true, false. Okay. We should perform linear regression. And the slope will be, oh dear, I need a calculator. .6333. Okay, so true will be A and B will be false. Okay. Yeah, so go ahead, feel free to discuss this. Okay, we'll say 10 more seconds, or maybe just five more seconds. And okay, so we'll stop there. Let's see. Nope, where did this thing go? Okay, and the actual answer is B. Oh, okay. So now I've pissed all of you guys off. All right, so what's going on? Okay, this, I have deceived you because yes, if we did slope, it would be r times sy over sx. That is correct, and you would get, 0.95 times 2 over 3, and you would get 0.6333, okay? the key part was we should perform linear regression, okay? How do we know we should perform linear regression? We have to create a scatter plot, and no scatter plot is present, okay? So we cannot say true that we should perform linear regression without creating a scatter plot first, okay? So we cannot say that linear regression is correct without creating a scatter plot. Okay. It would be true if I said, you look at the relation, the correlation is R.95, and I say a scatter plot shows a linear relationship. Okay, if this was included in there, then we would be okay. All right. Sorry. Well, at least I've tricked you here, and so if a similar question were to show up on an exam, at least you've, it's like fool me once, should not be fooled twice, right? Okay. Okay, all right, and then so lastly, okay, so we will say you perform linear regression analysis, or we'll say, okay, you investigate the relationship between x and y. There is a linear relationship, or linear trend. R is equal to 0.95, okay, and then we'll say the regression line is y hat is equal to 2 plus 4x, okay. All right, so I'll say true or false, okay. Slope interpretation. Will be that increasing x by 1 causes an increase in y of 4. Okay. Or I don't know. Increase of 4 in y, maybe that in terms of word syntax makes more sense, but causes an increase of 4 in y. Okay. So this will be our last. So you can discuss amongst each other and say, is this what the slope means? Y hat is equal to 2 plus 4x. Increasing x by 1 causes an increase of 4 in y. I mean what I have written there. You can. Okay, we'll say 10 more seconds to get your clicks in. Okay, I'm gonna click stop here. I feel like I'm gonna make many students upset again. And the answer here is false also. Okay. I'm so terrible. Okay, let me explain. All right. So here's the important part. Okay, there are two key things as to why this is wrong. Okay, one says causes. Okay, and so linear regression, correlation, and linear regression say nothing about a causal relationship. Okay, so even if you have a very strong trend between x and y, it does not mean that x causes y or that y is caused by x or y causes x. We can't make any of those conclusions. All we can say is that these two things seem to be happening together, okay? For example, if we looked at different nations around the world, there would be a strong correlation between cell phone infrastructure and expected lifespan, okay? And we would see that in certain nations where the cell phone infrastructure is very well developed, lifespan is high, and in other nations where cell phone infrastructure is undeveloped, life expectancy is expected to be low. Does that mean that the key to longer lives is build more cell phones? No, we know that's clearly not the case, okay? And then the other key here is that so the correct interpretation would be increasing x by 1 increases our estimate of y by 4. Our estimate of y, so we can just say y hat by 4. So increasing x by 1 increases our estimate of y by 4, and that's fair to say, okay? So if we increase x by 1, we estimate that y goes up by 4. But there's nothing about cause and there's nothing about actual values of y changing, okay? So that's the difference there. Sorry for the trick questions and the clickers, but it's just so to kind of drive the points home, and that way on actual exams you'll know the difference. All right, have a great weekend.